In this lesson, we're going to talk about how to graph rational functions where the numerator and denominator are both linear. There are two main situations with functions of the form f of x equals ax plus b over cx plus d. In the first situation, all of the x terms cancel out after factoring and simplifying. We'll do one example of that, then move on to the second type of situation and do a couple of examples there. In the second situation, the x terms remain in the numerator and denominator. So, example 1, suppose the x's cancel out of the numerator and denominator. An example of this would be if we wanted to graph the curve y equals 2x minus 10 over x minus 5. Well, we can factor out the 2, and then we're left with just x minus 5 over x minus 2 times the quantity x minus 5 over x minus 5. When those cancel out, we see we have y equals 2. So basically, we're just going to graph y equals 2. And we're going to put a hole where x equals 5. Fairly straightforward. There are no asymptotes. It's just a straight horizontal line. And, of course, we've got that hole right there. Now, in the second situation, the x terms don't cancel out. Suppose we want to graph the curve y equals 3x plus 5 over 2x minus 7. Okay, before going into this solution, let's just note that generally speaking, if we're graphing the curve f of x equals ax plus b over cx plus d, and if the x terms don't cancel out, then there's going to be a vertical asymptote at the value of x that sets the denominator equal to 0. Well, if cx plus d is equal to 0, then cx is equal to negative d, and x is equal to negative d over c. So in the case where the x's don't cancel out, we'll have a vertical asymptote at x equals negative d over c. And then, of course, since we still have x's in the denominator, and we've got the same degree in the numerator and the denominator, that means that we're going to have a horizontal asymptote at y equals lead coefficient over lead coefficient. Well, the lead coefficient of the numerator is a, and the lead coefficient of the denominator is c. So we're going to have a horizontal asymptote at y equals a over c. Okay? Now, the x terms in this case don't cancel out, so we've got a vertical asymptote at x equals 7 over 2. And we've got a horizontal asymptote at y equals 3 over 2. So we can, sketch those two asymptotes as you see here. Now we can also determine the x and y intercepts. To determine the x-intercept, we simply let y equal 0. So we put a big 0 there. And then multiply both sides by 2x minus 7, which would mean 0 is equal to 3x plus 5. And then 3x is negative 5, x is negative 5 over 3, and we would see that the x-intercept is at negative 5/3, and we'll just indicate that right there. We've got an x-intercept. To determine the y-intercept, we're going to let x equal 0. So letting x be 0, we get negative 5 over 7, and we now know what our y-intercept is, and we can indicate that on the graph as well. Now, we can plug in more x values to determine more points on the curve, and there's nothing wrong with doing that, but let's take a more elegant approach. Now, first what we're going to do is what's called a horizontal asymptote analysis. What we're going to do is we're going to let x be a number far to the right of any breaks in the domain. Now, there's only one break in the domain. In other words, there's only one x value where this curve is undefined, and that's at x equals 7 over 2. So what we need to do is let x be a value far to the right of 7 over 2. And I think the number 100 would satisfy. Okay? 100 is definitely way, way out there to the right. So letting x be 100, we see that y would be 305 over 193. And that's approximately equal to 1.58. Now, what's significant about that is our horizontal asymptote is at y equals 3 over 2, which is 1.5. So in other words, when x has a value of 100, the y coordinate is a little bit bigger than the y value of the horizontal asymptote. In other words, to the far right, which is what x equals 100 is, to the far right, the y value of the curve is above the y value of the horizontal asymptote. So this means that as it says in red, the curve approaches the horizontal asymptote from above to the right. We're approaching the horizontal asymptote this way as we get to the far right, not this way. Okay? So we can put a little arrow there, as you see, and that means we know ultimately when we graph our curve that it should be consistent with that. Now, since we went to the far right, let's go to the far left. Since there's only one break in the domain, i.e. 7/2, we can let x be a value far to the left of 7/2. Well, 100 is far to the right of 7/2, negative 100 is far to the left of 7/2. So we're going to pick a number way out here, specifically x equals negative 100. When we let x equal negative 100, y is negative 295 over negative 207. And that's roughly equal to 1.43. Well, 1.43 is slightly less than 1.5. So what that means is that as we approach from the asymptote from the far left, we're going to be coming from below, not above. We won't be coming from above, we'll be coming from below. And so, as it says in red here, the curve approaches the horizontal asymptote from below to the left. And we can put a little arrow underneath the horizontal asymptote there. So we're kind of starting to see what this curve looks like. Okay, we're starting to get a pretty good idea, just like that. And we also want to do a vertical asymptote analysis, and sometimes this is referred to as an epsilon analysis. Now, we can take a look at the behavior on either side of the vertical asymptote. So what we're going to do is we're going to let x be a value barely to the right of the vertical asymptote, and then later we'll let x be a value barely to the left of the vertical asymptote. Before we go any further, just think about it for a second. Whenever you have a vertical asymptote, like we do here, that vertical dotted line, we know that the curve looks like this. It's going to infinity. Or maybe it looks like this. Maybe the y value is going to negative infinity. But it's one or the other. So in other words, we know that if we're just a smidge to the right, we're either going to have a really, really big y value, which would indicate the curve looks like this, which is what curves sometimes look like near vertical asymptotes. Or if we're barely a smidge to the right, we're going to have a curve, a high magnitude negative number, which would mean that we're heading towards negative infinity and going down like that. That's what vertical asymptotes look like. They look like one or the other. Obviously not both, because it would fail the vertical line test if it was both, but it's going to be one or the other of these two. And so our job is to figure out which one. Well, in my little discussion there, I said just a smidge to the right. The mathematical term that we often use for a little smidge, like I was saying, is epsilon. Epsilon is a very tiny positive number. It's as tiny as you think it might be, it's even tinier. It's to smallness what infinity is to largeness. So if I said to you, how big is infinity, no matter how big of a number you give me, no, it's bigger than that. Similarly, if I say to you, how small is epsilon, you can give me the smallest number you could imagine, 0.000000001, and I would say, no, it's even smaller than that. But it's positive, okay? So what we're going to do is we're going to let x equal 7/2 plus epsilon. That's going to put us just barely to the right of this horizontal asymptote. And when we let x be 7/2 plus epsilon, we're going to find out what y is. And y is either going to be a huge magnitude positive number, telling us that our vertical asymptote behaviors like that, or it's going to be a high magnitude negative number, which tells us our behavior's like that. Now we're doing 7/2 plus epsilon right now, which is the number on the right. In a moment, after we're done this, we'll do 7/2 minus epsilon, which will be just a little bit to the left. But we're not doing that yet. We're focusing our attention right now on 7/2 plus epsilon. Okay? Well, if we let x be 7/2 plus epsilon, then all we do is we sub that in for x. Okay? And so that's what we have here. And we distribute the 3 into the numerator, into the numerator's bracket and the denominator's bracket. And we do our, just regular distribution. This is what we get. This is what we get. And then we collect like terms. And in the numerator, we have 31/2 plus 3 epsilon. Just regular math, regular distribution, collect like terms. In the denominator, the 7 and the -7 cancel out, and we have 2 epsilon. Okay, so that's our y value. Now let's think about this. The numerator is positive. This is the value we got right there. Now the numerator is positive and approximately equal to 15.5. 31/2 is 15.5. Remember, epsilon is an extremely small positive number. So if it helps you to think of it, it's 15.5 plus 3 times 0.00000000001. As small as you want to imagine it, but it's even smaller than that. Okay, so basically we'll say the numerator is 15.5. The denominator is 2 epsilon. So 2 epsilon is an extremely small positive number. And so when we divide that numerator of 15.5 by that very tiny positive denominator, we're going to get an extremely large positive number. In other words, as it says in red, when we're barely to the right of x equals 7/2, y will be heading to positive infinity, because that y coordinate that we're getting from doing that is going to be huge and positive. Positive numerator, positive denominator. Okay, so that tells us that y is heading to positive infinity, just barely to the right of the vertical asymptote. Well, now let's go to the left. To the left of the vertical asymptote, since epsilon's a positive value, 7/2 minus epsilon will be just to the left. We let x be 7/2 minus epsilon. We plug it in. We do our distribution. We do our collecting like terms, just like normal. And we get this quantity right here. Now, let's think about this. Here's our quantity. Our numerator is 31/2, which is 15.5, minus 3 epsilon. So if it helps you to think of it, it's like 15.5 minus 0.00000000003. Well, that's basically 15.5. Now the numerator is -2 epsilon. Well, -2 epsilon is, since epsilon's a number like 0.0000000, etc., 1, -2 epsilon is like saying -0.0000000, keep on going, 2. So imagine if we took the number 15.5 and divided it by that negative. Well, if we ignore the negative for a second, we know that 15.5 divided by an extremely small number will be infinitely huge. But since we have a positive numerator and a negative denominator, that tells us that it's going to be infinitely huge with a negative magnitude. So that tells us, as it says in red, that when we're just barely to the left of 7/2, y will be heading to negative infinity. And we kind of suspected that it would just from the points on the graph. We kind of had a feeling looking at the behavior of the curve that it would probably do something like that. But we write it in. We've done our theoretical vertical asymptote analysis. And now we sketch the curve. Now we respect the behavior we respect the behavior near the asymptotes and the points. So we're going to have a curve that goes like that. I just kind of missed those 2 points, but it's hard to draw this with the thing I'm using. But on a piece of paper, it'll be easier. So you're going to do your best job drawing the curve, what it should look like. Now, make it symmetrical on both sides. It wouldn't make sense if you draw a curve that's like that to then on this side draw something like this. They're symmetrical. So just sort of have them look basically the same on both sides. Do your best with that. It does not hurt to put in extra points on extra x values. So since this x value is 3.5 here at the vertical asymptote, there's no harm in plugging in an x value of 4 or an x value of 5 or an x value of 3 or an x value of 2 and seeing what the appropriate y values are and drawing a curve that goes through those. But let's assume for a second we don't do that. We see that based on the information we have enough to graph a pretty decent curve. And it's symmetrical on both sides. Now that we've sketched that curve, let's state the domain and range in set notation, the increasing and decreasing intervals, and the positive and negative intervals in interval notation, and then also the equations of the asymptotes. Well, our domain is set of all x element of the reals such that x does not equal 7 over 2. And the range is the set of all y element of the reals such that, this should say y here, little typo, such that y does not equal 5 over 3. Okay, that's our horizontal asymptote at y equals 5/3, and here's our vertical asymptote at x equals 7 over 2. Now, let's look at our increasing intervals. We don't have any. No matter where we are on this curve, we're never moving downwards if we move to the right. Don't look at the direction of that arrow to make this decision. In other words, take a tiny step to the right and ask yourself, would you go up or down? And no matter where you are on this curve, if you take a tiny step to the right, you're going down. So our decreasing intervals are, as shown, negative infinity to 7/2 in union with 7/2 to positive infinity. Now, to determine the positive and negative intervals, it's useful to remember that the x-intercept is negative 5 over 3. So that x value right there is negative 5/3. Okay, so our positive intervals, I'm showing them in red. That all those y coordinates are positive and all of these y coordinates are positive. So we can say negative infinity up to that value of negative 5 over 3 as well as 7 over 2 to positive infinity. Now the negative interval is in between, and that's the portion that is still in blue. That's from an x value of negative 5 over 3 to 7 over 2. Now make sure not to include a square bracket around negative 5 over 3. And the reason is, at negative 5 over 3, y is 0. 0 is neither positive nor negative, so you cannot say it's in the you cannot say the x value of negative 5 over 3 should be in the positive or the negative interval. Okay? And also make sure not to include a square bracket around 7/2 because x never equals 7/2. It's a vertical asymptote. And we never have a square bracket around negative infinity or infinity. We have a horizontal asymptote at y equals 3 over 2 and a vertical asymptote at x equals 7 over 2. All right, now let's graph this curve here. X squared minus 5x plus 4 over x squared minus 3x plus 2. And you might be saying to yourself, whoa, I thought we were doing only linear over linear here. Well, in this case, you'll see that after we do our factoring, we cross out those x minus 1s. We're going to have a hole at x equal 1. But then after that, we're going to be basically graphing the curve y equals x minus 4 over x minus 2, keeping in mind that hole. So this still sort of qualifies as the describing it the way I did at the start. So we do our factoring like we showed you there. We cross out our x minus 1s, and we see that y is x minus 4 over x minus 2, so long as x doesn't equal 1 or 2. Now at x equals 2, there's a vertical asymptote because it set the denominator equal to 0, and then after crossing out, the x minus 2 was still there. At x equals 1, we've got a hole because of the fact that it crossed out. Okay, so and we also have a horizontal asymptote because we've got, after simplifying, degree 1 over degree 1, and the lead coefficient of the numerator is a 1, and the lead coefficient of the denominator is a 1, and 1 over 1 is 1. So we have a horizontal asymptote at y equals 1. Let's figure out the y coordinate of the hole. To figure out the y coordinate of the hole, we know, again, that the hole is at x equals 1, so we plug in x equals 1 to the remaining simplified version of the expression for y, we get -3 over -1, which is 3. So that tells us we've got a hole at 1, 3. Okay? It's easy to figure out our x-intercept. If we want to figure out our x-intercept, we just let y equal 0. Multiplying both sides by x minus 2 gives us x minus 4 equals 0. So x is 4. So there's our x-intercept in red at the bottom. And our y-intercept is obtained by letting the x value equal 0. -4 over -2 is 2. So we got a y-intercept at 0, 2. All right. So we got a lot of information. Now let's do our horizontal asymptote analysis. We're going to plug in an x value far to the right of any disruptions in the domain. Well, the only disruptions in the domain are x equals 1 and x equals 2. So we can plug in a value of x equals 100. That's way to the right. Let's see what's happening. Far to the right, we have y equaling 96 over 98 when x is 100. Well, 96 over 98 is barely less than 1. So what we basically got is an x-coordinate of 100 and a y-coordinate of approximately 0.98, barely less than 1. That tells us that the curve to the far right is below. So we're approaching the horizontal asymptote from below to the right. And you might be saying, what is the... and if you recall, the horizontal asymptote is at y equals 1. So when we say below, we're below a value of, our y value is below a value of 1. Now we can go to the far left. We let x be a number like -100, and our y coordinate ends up being 52 over 51. That's barely greater than 1. So that means the curve's approaching the horizontal asymptote from above to the far left. Okay? Now, our vertical asymptote analysis, this is our epsilon analysis. We know our vertical asymptote is at x equals 2. So we're going to let x be 2 minus epsilon, and then we're going to let x equal 2 plus epsilon. We're going to sub those into the original expression, and then we're going to find out if y is going to be heading towards positive infinity or heading towards negative infinity. And actually, rather than the original expression, we'll plug it into the simplified expression. It makes it a little easier to see. Okay, so let's let x equal 2 minus epsilon. That should say, instead of -2 minus epsilon, that should say 2 minus epsilon. Okay? So letting x equal 2 minus epsilon, and remembering that after we simplified, we had x minus 4 over x minus 2. We get 2 minus epsilon minus 4 over 2 minus epsilon minus 2. Simplifying the numerator, we get -2 minus epsilon. Simplifying the denominator, we get negative epsilon. Now, let's think about this. The value of -2 minus epsilon over negative epsilon has a negative numerator with non-negligible magnitude. In other words, what that means is -2 has magnitude. When we subtract epsilon from that, we're subtracting, some quantity like 0.0000, et cetera, 1. When we do that subtraction, we essentially still have -2 left. That's what we mean when we say the value is non-negligible. It still has substance to it. Okay, it's still fairly large, so to speak. The value of the numerator, so after doing this calculation, the value of that numerator is not precisely equal to -2, but for purposes of this discussion, we can imagine that it is -2. Maybe a simpler way of saying this is a value of -2 minus epsilon is just barely to the left of -2 on a number line. Okay, so if you have that kind of straight in your head, we can proceed. Now, since epsilon is always positive, the denominator of negative epsilon is negative. And we know that the value of epsilon is infinitesimally small. So this means the denominator of negative epsilon is a negative quantity of infinitesimally small magnitude. Remember, when we plugged in 2 minus epsilon to our expression, this is what we got. So when we divide a numerator with finite magnitude, just to remind you, this is the division we're doing. When we divide a numerator with a finite magnitude by a denominator infinitesimally small, we get a value of infinite magnitude. Okay? Take, for instance, 1 divided by something extremely tiny is essentially huge. So this -2 minus epsilon over negative epsilon will have huge magnitude. Now, since the numerator is negative and the denominator is negative, therefore the value of y will be positive. So this means that just to the left of the vertical asymptote, y is heading to positive infinity. Continuing with the second half of our epsilon analysis, let's imagine that we let x equal -2 plus epsilon, although this should say 2 plus epsilon. Let's let x be 2 plus epsilon. So plugging in 2 plus epsilon, we get 2 plus epsilon minus 4 over 2 plus epsilon minus 2, and we end up with -2 plus epsilon over epsilon. So let's picture this. We've got a numerator that all of the significant magnitude comes from the value of -2. Perhaps an easier way of saying that is what's just below it. A value of -2 plus epsilon is barely to the right of -2 on a number line. We have a denominator of epsilon, and so since epsilon is always positive, we know the denominator is a positive infinitesimally small number. So what we're going to have is a negative numerator of magnitude over an incredibly small positive denominator. That's going to give us a negative number of huge magnitude. When we divide a numerator with a finite magnitude by a denominator infinitesimally small, we get a value of infinite magnitude. Since the numerator is negative and the denominator is positive, therefore the value of y will be negative. This means, putting those together, we have a value of infinite magnitude that's negative. This means that just to the right of the vertical asymptote, y is heading to negative infinity. Putting all that together, what we're going to do is make a graph with a vertical asymptote at x equals 2. We're going to make sure to the left of the vertical asymptote, y goes to infinity. To the right of the vertical asymptote, y goes to negative infinity. We'll have a horizontal asymptote at y equals 1. We'll approach that horizontal asymptote from below to the far right, and we'll approach it from above to the far left. We'll have an x-intercept at 4, 0, a y-intercept at 0, 2, and a hole at 1, 3. Putting all that together, this is the curve we get. Now, we want to state the domain and range in set notation, increasing and decreasing intervals, positive and negative intervals, and equations of asymptotes. So, our domain is going to be x cannot equal 1 or 2. It can equal 1 because we've got the hole there, and it can equal 2 because we've got the vertical asymptote. Our range will be y cannot equal 1 or 3. It can't equal 3 because of the hole, and it can't equal 1 because of the horizontal asymptote. Our increasing intervals, you might be tempted to say, well, our increasing intervals are from negative infinity to 2 in union with 2 to infinity. But that wouldn't be true because the curve's not defined at x equals 1. So we actually have to say negative infinity to 1 in union with 1 to 2 in union with 2 to infinity. There are no decreasing intervals. At no point on this curve, if you take a minuscule step to the right, will you be going down. Our positive intervals. Again, based on what we did in the last one, we might be tempted to say, okay, well, everything's positive here and everything's positive here. So we might be tempted to say negative infinity to 2 in union with 4 to infinity, because if you recall from a while ago, our x-intercept was at 4. But we can't do that because there's actually a hole here and the curve's not defined at x equals 1. So instead, we have to write it like this. X can go from negative infinity to 1 in union with 1 to 2 in union with 4 to infinity, and that takes the 1 out of here. It would be wrong to say negative infinity to 2. And our negative interval will be 2 to 4. That's this whole region here. Those are all negative y values. We have a horizontal asymptote at y equals 1 and a vertical asymptote at x equals 2. And that's the end of that slideshow. So hopefully that was educational.